And all right, ladies and gentlemen, today's class recording has started. So we are going to use the demonstration that we did off camera, even though there's no real camera, it's just the screen. But so we did the demonstration with the glass into the bed sheet, right? And we tossed it into the bed sheet a couple of times, or Lexi tossed it a couple of times. But regardless of how hard she threw the glass, nothing happened, right? Lexi, if you would have done that demonstration without the bed sheet, just the very first toss where you tossed it underhand, right? What would have happened to the glass when it hit the ground? It would have shattered, right? But then we gradually increased how fast we threw that glass, and it still didn't shatter the whole time, all right? So today we're going to talk about momentum and impulse and look at some examples of why the glass didn't break and how that applies to things that we see every day, things you're really familiar with, and why all those things happen. So we're going to start off. I'm going to go actually in a little bit of a different order than on your outline because I think that it suits better. So we're going to start off actually right in the middle of the page, Roman numeral number 1, letter D, and we're going to look at Newton's second law. Okay? So we've talked about Newton's second law several times. We said that Newton's second law tells us about what? What does Newton's second law tell us about or describe for us? Newton's first law tells us about what? Inertia. Newton's second law tells us about and acceleration, right? So Newton's second law tells us about acceleration, and it tells us that there are two factors that affect the acceleration, right? Those two factors being mass and net force, right? And that different kind of relationships exist between the force, mass, and acceleration, right? Force and acceleration are directly related. Mass and acceleration are inversely related. And all of those things are true. But there's one more factor that today we're going to include in our discussion that is an important factor because while we talk about big forces cause big accelerations, and yes, that's true, how long we apply that force is important to determine what actually happens in a situation. Let's think about a rocket ship. A rocket ship has a big, huge engine on it. And yes, it has a lot of mass, but that big, huge engine can apply a big, huge force. But if we only applied that force for like 0.1 seconds, would anything be that different? Even though it's a big force, yes, that big force causes a big acceleration, but if we apply it for a very short time, there isn't a whole lot of change to our situation. Okay? So here's what I'm going to do. I'm going to take Newton's second law, and I'm going to bring in something that we talked about previously in the previous unit. And let's talk about acceleration. How did we define acceleration? We know what causes acceleration, right? But how did we define acceleration, or what is acceleration? Change in velocity over time, right? So A is equal to delta V over T, all right? And I'm going to take that expression for acceleration and substitute it into the Newton's second law in the place of acceleration. Good there? And then I'm going to do a little bit of algebra, nothing too difficult, and end up with this. Does that make sense how I got from step 2 to step 3? You can see that? Just multiply both sides by t. And I end up with this expression down at the bottom, which is going to be the basis for our discussion today. So that equation down at the bottom, we refer to as the impulse momentum equation. And the impulse momentum equation is written right up here, right? I included in this version of it, this delta in front of t. You don't have to put that delta in there. You can just make it sigma f times t is equal to m times delta v. Okay? So sigma f times t is equal to m times delta v. And that's Roman numeral number 2, letter A, right? That's our impulse momentum equation. And as you can see, impulse momentum equation relates for us how much force do we have acting on that object, but then how long does that force act on an object? That's the key factor that we're going to explore a little bit more today. So how much force, how long is that force, and then how much does the motion actually change because of the force and the time that we apply that force. So not just a relationship between force and acceleration, but a relationship between force time and the resulting change in the motion, or delta v. All right, good there for starters? Going to take a couple more seconds to finish writing that down. Before we fill in any more of the outline, let's talk about a couple more examples. Okay, got it? Okay, flip it over to the back side, and let's talk about this picture that shows up at the top of the back. This picture up at the top of the back is just a different version of the demonstration that we did at the beginning of class with the glass and the bed sheet. Okay? So, 2 eggs dropped from the same height. So let's say they get dropped from the green line that shows up there on the top. Okay? So, from green to yellow, what happens to the eggs? They accelerate, and they go faster. Right? And as we look here, we can kind of see that if we look at the spacing between these pictures, right, the eggs are getting a little bit farther and farther apart, and we talked about that in the last unit. That means it's speeding up. Okay? If we assume that even though the right-hand side of the picture doesn't quite show those intervals quite as well, right? If we dropped both eggs from the same height, what can we say about them when they get to the yellow line? What do we know that gravity does to all objects? Accelerates them, but accelerates them the same, or at this case, 9.81, right? So when they get to the yellow line, both of them are going exactly the same speed. Good? Okay. Then, from yellow line to red line, what happens in both pictures? There's more acceleration. What kind of acceleration now from yellow to red? Because physically, what's happening to those eggs? They're not quite changing direction because they don't bounce. What do? They stop, right? From yellow to red, both of those eggs are going to stop. Okay? Oh, by the way, I have a bunch of stuff for you to write down here, so now you can just listen, and then we'll talk about putting it all together in a second. Okay? All right, from yellow to red, both of those eggs are going to stop. However, if we had to take a guess, which one experiences more force during the stopping process? Probably the braking one, right? Because it broke, whereas the first one didn't. All right? So let's talk about why that happens. When we go from here to here, there is a change in velocity. At the yellow line, hold on, don't write anything yet. Promise. Just I'll explain it all, and I have a little summary. Let's just make sure we get it down first. Okay? So the yellow line, they're going the same speed. The red line, they're stopped. That's negative acceleration. And if there's negative acceleration, there has to be what? A net force, right? So in the case of the picture on the right, what is supplying the net force to make the egg stop? The pillow. In the picture on the left, what is supplying the net force to make the egg stop? The plate. Okay? Obviously, those are two different objects. One's soft, one's hard, right? But let's talk about why that results in what we're seeing. The egg hits the pillow, and the pillow applies a force. But what happens to the pillow as the egg falls into it? It like indents. It forms around the egg, right? And as a result, the pillow starts hitting the egg, but continues to hit that egg the entire time that it's cooshing down into it, right? The plate doesn't have that same kind of give to it, right? The egg continues to fall until it hits the plate, and then it stops, like that. All right? So we said that in the impulse momentum equation that we just looked at on the previous side, we introduced a new factor, and that factor is time. What's happening, how much time does it take to stop the egg with the pillow versus the plate? What's different about the time? Jenny. It's a longer time to stop the egg with the pillow than it is with the plate. Okay? We said that in both cases we have to accomplish the same thing. We have to stop the egg. If you have a longer time to accomplish that stopping, what happens to the amount of force that you need? If you have a longer time to do something, do you have to use as much force? No. But if you have to do something in a very short period of time, that amount of force is increased, right? If we think about it, if you want to think about it like real life situation, right? If you have a paper due next week and you do little bits at a time, right? You don't have to work as hard in those little bits. But if you do all of it the night before, guess what? You got to work harder, right? Not saying anybody does that, but I'm just saying, I'm not accusing anybody, but, you know, think about it that way. Sophia, go ahead. Actually, both. And that's Newton's third law, and we'll talk about that next week. But let's talk about what they're doing to the egg, right? The force that they are supplying to the egg. Because the egg is really what's feeling the force in this case, right? Okay, so let's summarize, okay? We're still going to use this equation that we just wrote down on the previous page. And we referred to this as our impulse momentum equation. Okay? This situation right here, from yellow to red, in both cases, delta V is going to be the same from my yellow line to my red line. Does that make sense that in both cases the change in velocity is the same? If we drop them, they're both going the same speed when they hit yellow, and eventually they're going to stop at red. So delta V is the same in both cases. Kara, go ahead. This is where you want to probably say, yeah, right. That's right. So now. When the change in velocity is going to be the same, force and time have an inverse relationship. Now, when delta V is the same, a lot of times this applies when something is stopping. Because eventually, what's the final velocity going to be? 0, right? So we know that that has to happen. So the delta V is going to be the same, like in this case right here. Or when we talked about the tossing of the glass into the sheet. Regardless of how fast Lexi tossed it, eventually it's going to stop, whether it hits the sheet or whether it hits the floor. Okay? Inverse relationship means what? What's the gist of an inverse relationship? One goes up, the other one goes down, right? So, in this case, right, if we have a longer time to bring that egg to a stop, we don't have to apply as much force. The pillow, because of the way that it moves or the way that it squishes when the egg falls into it, has a longer amount of time to bring this egg to a stop than the plate does that has to stop it, boom, as soon as it hits the surface. More time, less force. Less time, more force. So the one factor that keeps the egg from breaking or that keeps the glass from breaking is the increase in time. What happens to the bed sheet when the glass ran into it? Did it stay right where it was? No, it like cushed with the glass when it fell into it, right? Or when it was thrown into it. That increases the time that it takes to stop that glass. If you increase the time, you don't have to use as much force. Okay? Does that make sense? So, another practical example. Right? Airbags and seatbelts. Okay? What does the airbag or the seatbelt do to you? It stops you, but what happens while it's stopping you? It's like stopping your inertia, right? But what else can stop your inertia? The wall or the dashboard, boom, that you run into, right? But how long does it take the airbag to stop you? Is it a long time? Not really. Is it longer than running into the steering wheel of the car? Yes. So in this case here, why do airbags save you in a crash? Eventually, and we talked about this last week, right? Why do you get thrown forward when you're in a car crash or if you get hit head on? The car stops, but you keep going. That's your inertia, right? Okay? Eventually, what's going to happen to you? Eventually, regardless, you're going to what? You're going to stop eventually, all right? But the longer that it takes to bring you to a stop, the less force is required. All right? Does that make sense? Okay. So, this discussion came up in the other class, and hopefully it will kind of make some more sense. Okay. When we talked about the your inertia in a car crash and stuff like that, somebody asked, "Is that a concussion?" And the answer is yeah. A concussion happens when, sorry, if you have like PTSD, you can leave the room. That's fine. So, okay. So I'm being serious. If it makes you uncomfortable, you don't have to stay. So, okay. A concussion happens when your head stops, but your brain keeps going. Your brain's not attached to the inside of your head. There's fluid in there. It's not a lot, but it's not attached. If your skull, your bones stop because you run into a wall or a head, somebody else's head or a hand or the ground or whatever it might be, your head stops, but what does your brain keep doing? It keeps going, and it runs into the front of your skull, and that's, or the side of your skull, or however you which way you get hit, right? That's a concussion, right? Now, along those same lines, when we talk about football, but that's just kind of the most relevant one at this point in time, like, oh, well, people well, can't we make a better helmet? A helmet doesn't protect you from a concussion. What does a helmet protect you from? Cracking your head open, right? The outside of a helmet is hard. The outside of a helmet is hard, and this is a football helmet, but it's also a bike helmet or any other helmet that you wear, right? A football helmet is hard on the outside, but what is it like on the inside? It's an airbag for your head, right? When your head hits the ground, it's gonna stop. The helmet increases the amount of time it takes for your head to stop. So there's less force applied to your head, and that protects what from happening? Cracking your head open. It prevents your skull from fracturing. Helmets protect your skull and the bones. They don't protect your brain because your brain is not attached, right? There's only a little bit of room in there between your brain and your skull, and that's why the helmet doesn't help you with the concussion. Your brain is still going to keep going. Okay? Does that make, are we okay with, like, why? Don't have your skull change directions quickly. Like that's what prevents a concussion. Yeah, John, go ahead.
What if you put something inside of your skull?
Right? If you could put, now, that's actually, right, that's what you would have to do. Like if your brain, see, the problem is, yes, your skull is not attached to your brain, but there's not a lot of room in there, right? If your skull was like a fishbowl, and like your brain was only this big, but your skull was this big, yeah, your brain could move around a lot in there and probably wouldn't hit your head, right? Now, the problem with that is your brain is also attached to your spinal cord. So if your brain's allowed to flop around inside your head, the chance of your spinal cord breaking is increased, and you don't want that. You know, that's kind of important, you know, so. Okay. So yeah, that's what would have to happen. But the other thing too is that your brain is soft. So even if you stop the front of your brain, what is the back of your brain trying to do? Keep moving, right? This baseball, when it hits the table, all of it basically stops at the same time because it's solid, right? But if we were to take a water balloon and drop it, right? The water balloon goes like this because that was an actual sound effect. That's what it sounded, right? So, yeah. Yeah, because it's not solid. Yes, but yep, a lot of well, actually, when your concussion, why your neck is sore, a lot of times has to do with not so much the injury to your spinal column, but the mechanism that your head hits. It's whiplash, and so somebody talked about whiplash. So, like, what is whiplash? Whiplash is when you're in a car crash and you get hit from behind and your head does this, right? But is your head really getting thrown backwards? No. When you're sitting in a car, right? A lot of times you get whiplash when somebody runs into you from behind, right? When you're sitting in the car, everything's sitting still. If somebody hits you from behind, the car that you're sitting in starts moving forward. Well, but it also hits you because of the seat, right? Your body starts moving forward, but what is your head trying to do? Stay where it is. So when you do this, it's not because your head got thrown backwards. What actually happened? Your body went forward, and your head's just trying to stay where it is, right? Or so that hurts your neck because of that, right? The same thing, like, you know, if whatever it is, how you get your concussion, a lot of it is because your head gets whipped around. Well, it seems, I mean, you know, no comments. Okay, good.
Hilarious.
Well, Like by doing this?
Well, like, I don't know, like, if you're, like, thinking in your head.
I don't know. I'm not like you get dizzy from doing that, you know, because that's actually you have little tubes in your ears that are filled with fluid, and that's how they work. Like as your head moves, the fluid is trying to stay where it is, and that's how you like balance. But I'm not sure if you can like just shake your head and give yourself a concussion. I'm not. Okay. If you don't,
My doctor has a kid who I guess was an addict and he was shaking his head really, really hard at a concert, and I'm like,
sweet. So there you go. That's a first-hand account. So, I mean that is the mechanism, right? If your head is moving forward and you stop your head with your muscles, but your brain keeps going, that's how a concussion happens. No, but like what? Well, yeah. Like I mean, like if you like, could it? Probably. Right. So, yeah. Now, the other thing too, right? So going back to the airbag thing, the airbags and seatbelts increase the time, so they decrease the force, but it's not a long time. If you have ever met or know somebody or been in a car accident where the airbag deployed or the seatbelt like really saved you, if you look, yeah, it can leave, it can break your collarbone and it can leave a big burn across your chest. All right, how? Because what is your body trying to do? Well, until you know.
Until you fly. There's more risk of you like dying in a car accident than
Very much so.
What if the plane crashes? You're dead.
That's a cool story though.
In the ocean.
So,
In the ocean, you get
but the idea being there, the seatbelt is increasing the time and decreasing the force. It's not like falling onto a trampoline, right? Or falling into like one of those big jump houses. That's not what the airbag's like. It decreases the time, it increases the time a little bit, which decreases the force a little bit, but it's enough to keep you from getting killed. Yeah, like dead, right? So.
I just thought this is so awesome because for 50-year-old man, the way that most of them rate their spines is when they're heading down Titus River Lane and they sneeze.
So.
It's so much fun.
I have some time before I have to worry about that. So. I have a little bit of time before I have to worry about
not again.
But no, that is, people do get hurt that way. Like, all right. So let's take a look at this equation again. Name some parts, okay? It's called the impulse momentum equation, so let's name certain parts. So impulse, by definition, impulse causes a change in the object's momentum. And if it's going to change something, it needs a force. Right? Forces cause things to change. Sorry, front side, Roman numeral number 2, letter D down at the bottom. Right? The impulse is caused by a net force applied for a certain amount of time. Either the greater the net force or the greater time we apply that force will increase the impulse. Impulse is sigma F times T. You can throw the delta in there if you want to in front of the T, or if you just want to make it T, that's fine too. Technically, time is an interval, so it's a delta T, but that's okay. So if it's the impulse momentum equation, one side of that equation is impulse, the side that has force and time on it. That means the other side is the momentum side. We define momentum as the mass times the velocity. This is up at the top of the page, very, very top. I told you we were jumping around a little bit. So the instantaneous momentum depends on the mass and the instantaneous velocity. We calculate the momentum of an object by multiplying m times v, its mass times its velocity. We use the letter P to represent momentum. I know that seems weird. The way that I've heard it, and I don't know if this is true or not, but when the idea was being developed, and like back in the 1600s, Newton, that kind of thing, they kind of referred to this as the progress of the object, not the momentum of the object. So that's like where the P comes from, right? But important, and this will be important when we start doing lab next week. Momentum is a vector quantity, right? It tells us two things: how much momentum it has, its magnitude, but then also which way is it going. That's important when we're talking about the momentum. And because it depends on velocity, hopefully that makes sense. All right, good there? Let's take a look at one more picture before the end of the period. So let's take a look at the back, and let's take a look at this guy swinging his golf club. Okay. While this is a picture of somebody swinging a golf club, this explanation can apply to pretty much any kind of athletic endeavor, or if you're just talking about like jumping or walking, it applies as well. So this could be swinging a golf club, but it could also be hitting a baseball, throwing a football, kicking a soccer ball, hitting a tennis ball, and playing basketball with when you shoot the ball. Okay, all of those things apply. So when we talk about this idea of follow-through, when we shoot a basketball or we hit a baseball or we kick a soccer ball or whatever it might be, as soon as we make contact, you don't just stop, right? We continue that motion through the process of the whole thing, right? Does that make sense? That was very poorly worded, but do we understand what I'm saying, right? So, if we take a look here at this equation again, okay, in the case of hitting this golf ball, what do we usually want to do with delta V when we're hitting this golf ball? Well, when we hit a golf ball, let's say we're like driving the ball off the tee, what do we want to do with delta V? Do we want it to be big or small? Kind of big, right? Depends on what kind of shot we're hitting, all right? But that'll be a good discussion point here. Let's say the very first shot in a hole, we want to try and hit the ball as far as possible, right? We generally want to make delta V as big as possible, okay? So we use a big force. That's how hard you swing. But we also want to increase the time that it takes, or that we are applying that force. By following through with our motion, we increase the time that we are applying the force. Or when we follow through with our hands, when we shoot a basketball, right? By bending your wrist, you're increasing the time that you are applying the force to the basketball. Or even think about jumping. When you jump in the air, first thing you generally do, if you're trying to jump as high as possible, first thing you do is bend your knees, right? Because now you're pushing off the ground. But when you bend your knees, you have to straighten your legs out. That increases the time that you're pushing off the ground. So if we make the force big and the time big, the other side of the equation has to increase to keep up, because that's what an equation is, right? Two sides equal. So if we make force big and time big, that makes delta V big. And that results in a longer hit or a longer throw it might be. Okay? Alright. We will pick up with this on Monday. We'll look at some lab applications of this. We'll do some lab together on Monday and go from there. Okay? I'll update the calendar over the weekend. I will add a couple of reading things and a couple of homework stuff from the book just to reinforce these ideas. And we'll take a look at that more on Monday.